All right, so we're going to be doing Chapter 7, Question 1 here. Chapter 7, Question 1. All right, so it asks a little bit about the periodic table. What element would be expected to have chemical and physical properties closest to that of fluorine? All right, well, we've mentioned this before, and there's no surprise that the periodic table here, that the relationship between the elements on the periodic table, if it's in the same row, then they're chemically similar. Our standard example is the reactivity of sodium all the way down to the reactivity of cesium. You put sodium into water, you put lithium into water, anything over here in the alkali metal range, and it's very explosive or very reactive. In the case of lithium and sodium, just kind of a fizzle. But as you move down, you get bigger and bigger reaction, as we've seen before, and as you can see all over YouTube videos. And so, essentially, the take-home message that same column, very similar properties. All right, even if they're close to each other in a row, you'll have kind of similar properties. Not as similar, but same column, very similar. So, if we look at which element would be expected to be most like fluorine, the ones that are most like it are the ones that are in its family or in its column, and so that would be chlorine or iodine or bromine, right? Okay. Which set of elements would all members be expected to have very similar chemical properties? All right. So again, it's likely going to be a group which is very close on the periodic table. Very same row would also be very possible or similar as well. So we see the bottom, or one of them says neon, sodium, and magnesium. Now, neon's a noble gas. It's like helium, argon, krypton, and so forth. Sodium, it's not. It's an alkali metal. Magnesium, it's an alkaline earth. So not very similar. But we can look at those different trends there. Oxygen, sulfur, and selenium. Those are all in the same row, right? Column. All in the same column. All in the same family. So they're going to be the ones that are most similar to each other. Whoops, what was that one? That was, move back to that one real quick. That was Chapter 7, Question 1. We have one twice. Oh, 2 Chapter 7 questions, 1. The algorithmic and the multiple choice. All right, so now we're moving on to problem 7.8. All right. The prefix ika comes from the Sanskrit word for one, and Mendeleev used this prefix to indicate that the unknown element was one place away from the known element that followed the prefix. For example, ecosilicon, which we now call geranium. All right. But Mendeleev also predicted the existence of ekamanganese, which was not experimentally confirmed until about 1937. Or because this element was radioactive and hard to come by, right? Radioactive means it will break down and become a different element, which is something that we'll talk about probably more in 106, but I'm sure you've heard about it in other classes. And it doesn't occur in nature. So based on the periodic table, what do you think the element that Mendeleev was referring to as ekamanganese? So we go to manganese on the periodic table, 25, and eka, according to at least his reference to silicon to geranium, meant one below, or just one difference. And so we can look at technetium, and we can see that technetium, I don't know if you have, your periodic table might not identify it specifically as radioactive, but it is radioactive. Now, one way that we can identify radioactive chemicals is, if you look at the periodic table, their mass numbers are generally in parentheses, like this. All right? So when a mass number is in parentheses, that's because that's the suspected mass, but it's always degrading and changing. The mass of that element is not stable, it's always changing. So that's one way to identify it as radioactive. It'll be in parentheses like that. Okay? So that's likely going to be technetium, your answer there. All right. Problem 7-.11. So what is meant by the term effective nuclear charge? All right, so your effective nuclear charge is, effectively the charge that an electron feels. All right? So if I think of an atom, here's the nucleus, and here are the electrons. Right? The nucleus is a group of positive charges, and the electrons are around the nucleus because they're being drawn to that nucleus. Electrons are negative charges, they're being drawn to that nucleus. Now, as electrons come close to the nucleus or are in a closer proximity, then they, in a way, you could think of, absorb that positive charge. And so the outer electrons in outer shells, are going to feel less of a draw from those protons in the nucleus. So effectively, these outer electrons don't feel as much of a draw as the innermost electrons do. All right? So that's one way of saying the actual nuclear charge that they feel, or another way we say it is the effective nuclear charge. So that's what's meant by the term effective nuclear charge, and hopefully you can put that into words there. How does the effective nuclear charge experienced by valence electrons of an atom vary going from left to right across the periodic table? Well, going from left to right, starting, for example, from, we could go from scandium to zinc. Nuclear charge increases. Does that make sense? Is it true that the nuclear charge increases from scandium to zinc? Yeah, that makes sense. Scandium, element 21, zinc, element 30, right? We're in the 3D, right? The first row of the D block. Scandium to zinc, the nuclear charge increases. The nuclear charge is simply the number of protons, the positively charged in the nucleus. That's the nuclear charge. Positive charges here in scandium is 21. Positive charges in zinc is 30, right? So the number of positive charges increases. So you have an increase in the positive charge. So it's true that to say from going from left to right, the nuclear charge increases. Now the effective nuclear charge is a different story, right? Does the effective nuclear charge increase? Well, let's think about it. If the effective nuclear charge is to increase, then that means the electrons have to be positioned in such a way that they'll all still have, be able to feel or be able to be drawn by that nuclear charge. All right? And that's true if you look across a single subshell, like scandium, the 3D, going from scandium to zinc. Because all of those electrons that are going into this subshell, scandium to zinc, all of those electrons are going in the same 3D orbitals. They're all the same distance from the electron. And so all of them are feeling essentially the same amount of pull on the nucleus, and because of that, their effective nuclear charge is also increasing as you go across to the right. All right, so going from left to right across the period, nuclear charge increases while the number of electrons in the core is constant. The result is an increase in Z effective. Now, that's not true that the electrons are constant. The electron, electron in the core, that's right, the electron in the core is constant. So going from left to right across the period, nuclear charge increases while the number of electrons in the core is constant. This results in an increase in Z effective. Second choice, going from left to right across a period, nuclear charge remains approximately the same. So that's not true. The nuclear charge doesn't remain the same. Going from left to right across a period, nuclear charge remains approximately the same while the number of electrons in the core increases. No, the number of electrons in the core, now, what does this mean, the core? Let's see, are we on the right? This is problem 7-11. Yeah, let's draw our core, our nucleus. So a reminder of what the core means. Let's look at magnesium and talk about what core electrons are. So we know if we want to draw the electron configuration for magnesium, you go 1s2, 2s2, P6, 3s2. That is the electron configuration for magnesium. The abbreviated electron configuration for magnesium is neon 3s2. All right? And so this abbreviated electron configuration quickly helps us identify the core electrons and then also the valence, or the electrons that are outside the core. So in this case, the 3s2 are the two valence electrons that magnesium has. If I do one more example, let's do arsenic. Okay, here's arsenic. The electron configuration for arsenic: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, arsenic 3, 4p3. All right, so that's the electron configuration for arsenic. Now let's do the abbreviated electron configuration for arsenic: argon, and then after argon we have the 1, 2, 3, 4, 4s2, 3d10, 4p3. All right, so here is the electron configuration for arsenic. Here is the abbreviated electron configuration for arsenic. Now in the abbreviated, it's easy to see the electrons which are outside the core, again, outside the core. This is the argon core, and as these electrons move up and down, this core is going to be pretty much the same. 4s2, 3d10, 4p3. These are the ones that are outside. Are all of these valence electrons? No, just the ones that have the highest n value, or the highest value, which is 4 there. So 4s2 and 4p3, that's 5 valence electrons. And then these ones are called pseudo-valence electrons. Okay, so we wanted to show that so that we could think about the where our electrons reside in the shell, right? All right, so which one do we leave off on? Going from left to right across the period, nuclear charge remains approximately the same, while the number of electrons in the core increases. Oh yeah, we're talking about the number of electrons in the core. And the number of electrons in the core doesn't change. Okay, going from left to right across the period, nuclear charge decreases, while the number of electrons in the core is constant. This results in a decrease in Z effective. All right? So, that's not consistent either. So, it seems like the only one that follows our understanding of how electrons fill up orbitals and how the nuclear charge changes and how the effective nuclear charge changes is the one that says going from left to right, the nuclear charge increases. That makes sense. While the number of electrons in the core is constant, and that makes sense also. The electrons in the core stays the same, and the result is an increase in the Z effective on the elements as you go from left to right. And if you have a larger effective nuclear charge, then each electron is going to feel more and pull in tighter and get smaller. Okay then, so that. All right, so problem 716. On problem 716, let's see, it says arrange the following atoms in order of increasing effective nuclear charge experienced by the electrons in the n equals 3 electron shell. So we have potassium, magnesium, phosphorus, rhodium, and titanium, and we need to rank them from smallest to largest. Now, we're not smallest atom to largest atom, but smallest effective nuclear charge. Now, generally there would be a relationship amongst one row between the effective nuclear charge and the size, but when you're looking at elements that are in different rows, then that gets a little sticky. And so they kind of clarify this by saying n equals 3 electrons. So then we're always looking at the electrons which are in the same distance from the shell, from the nucleus, the same shell distance from the nucleus. Therefore, the only thing that's going to change the effective nuclear charge is the number of protons. So essentially we have to put these in order of the more protons are going to have the largest effective nuclear charge on the 3D electrons, and the fewer protons are going to have the smallest effective nuclear charge. So the thing that has the fewest protons is magnesium, The thing that has the most electrons is, or sorry, fewest protons is magnesium. The most protons is rhodium, and then you can just put them in order like that, from least protons, magnesium, most protons, rhodium, and that order should tell you the effective nuclear charge, because we're talking about the same electrons, just the 3D electrons. All right. So the next one here is Chapter 7, Question 6. Which one of the following has the smallest radius? Okay, so now radius is related to where it's at on the periodic table. The higher up, the smaller radius, because the lower you go down, the larger the shell that is being filled. The further to the left on the same column also has a larger radius. So if we look at strontium compared to iron, strontium compared to iron, iron is higher up and it's further to the right, so it's going to be smaller. So between strontium and iron, iron would have to be smaller. Between potassium and iron, which would be smaller? Well, potassium has less electrons than iron, but all of the electrons that are added in after potassium to make iron actually are going into the same shell, and the number of protons is increasing, so iron has a larger effective nuclear charge. So iron would be smaller there. Iron and bromine, which one would be smaller? Well, as you move to the right, bromine gets even more effective nuclear charge, and the size of bromine actually gets even smaller, right? So it looks like bromine is going to have to be smaller than iron. All right, which of the following atoms has the largest radius? The largest, right? So largest, we're generally going to be looking at the one that is lower down and further to the left if it's in the same row. So if we look at arsenic and tellurium, TD, where's arsenic? There's arsenic and tellurium. So tellurium's larger, right, because it's below arsenic. How about tellurium and selenium? Again, tellurium's lower, so that's got to be larger. Tellurium and antimony. Well, if you're looking at tellurium and antimony, the difference is just one electron, and that one electron is just going into a 1, 2, 3, 4, 5p orbital. So it's just another electron in the subshell that's exactly the same, but we have a whole other proton to make tellurium even smaller. So what's larger, tellurium or antimony? Antimony would have to be larger. Then antimony or sulfur, and antimony is definitely going to be larger. So I think we would have to identify that even though tellurium has more electrons than antimony, antimony would have to be larger because it has fewer protons, and so the effective nuclear charge on antimony is smaller than that of tellurium. All right, I hope you followed that. What's next? Chapter 7, Question 7. Okay, which of the following correctly lists the atoms in order of increasing size, smallest to largest? All right, so we can look at the beginning there. Is fluorine smaller than bromine? That's true. Fluorine is smaller than bromine because there's just fewer electrons, and the electrons in fluorine are in the second shell, whereas the electrons in bromine are in the fourth shell. So fluorine is smaller than bromine. Is bromine smaller than germanium? That makes sense too. Bromine is smaller than germanium. Let's see, the smallest to largest. Yeah, bromine is smaller than germanium because bromine has more protons, and even though it has more electrons than germanium, it's pulling those electrons tighter because all of those electrons are being added in the same shell. Potassium. Is potassium, let's see, bromine needs to be smaller. Is potassium, germanium, wait a second. Yeah, germanium's larger than bromine, so that's the right order. Now, is potassium larger than germanium? Potassium. So there's germanium, potassium. Potassium should be larger than germanium. That's right, because potassium is in the same row, but it's has a lot fewer electrons, but its effective nuclear charge is going to be very small because it only has 19 protons. And then rubidium has to be larger than potassium as well. So let's see, double check here. Going smallest to largest, right? So fluorine is supposed to be the smallest one there. So you can look at the other ones and see where there's some problems and find out and verify which one. Same logic, verify that we got the right answer. All right, the next one, Chapter 7, Question 10. Which of the following, which gives the correct order for atomic radius for calcium, potassium, arsenic, germanium, and krypton? All right, so we're looking for the correct order in terms of atomic radius. Well, we could identify what the larger one is, and it looks like it's going to be krypton, because they give us 3 choices, with krypton as the largest, right? No, that's not the real reason. But krypton is the furthest down in the periodic table, is that right? We have calcium, which is... Oh no, that's not right. Krypton, calcium and krypton are in the same row, so calcium is the... which gives order, let's see, which gives the correct order of atomic radius. So calcium is larger than krypton. Yeah, so that's right. So calcium has to be larger than krypton because calcium is in the same row as krypton, but it has fewer protons to pull the electrons in. All right, we can always double check with our table on page 255. Calcium larger than krypton. Oh, well that means that the only choice, well, no, let's see which one. So krypton is not the largest. Let's see, is calcium larger than potassium? No, that's not right. Potassium is larger than calcium. That's right. Is calcium larger than gallium? No, is that gallium or germanium? Germanium. Is calcium larger than germanium? Yes. Is germanium larger than arsenic? Yes. And arsenic is larger than chromium, krypton. So, Chapter 17, reading question 3. Sorry, Chapter 7, reading question 3. An atom of calcium is larger than an atom of gallium. One explanation is that compared with gallium, calcium has fewer protons and therefore, and is in the same, and the electrons of calcium and gallium are in the same shell, therefore it has fewer, calcium has a lower effective nuclear charge. So let's see what they say. A greater nuclear charge, calcium doesn't have a, let's see. Compared with gallium, calcium has a greater nuclear charge? No. A smaller atomic number? It does have a smaller atomic number, more unpaired electrons. Unpaired electrons don't have anything to do with electron size. A larger mass number. Calcium doesn't have a larger mass number than gallium. So, it would be because it has a greater, let's see. Compared with gallium, calcium has a smaller atomic number. All right. Number 11, which of the following is an isoelectronic series? Isoelectronic, what does that mean? Isoelectronic, electronic refers to electrons, and iso refers to electrons, the same number of electrons. So if we look at O2 minus, for example. O2 minus, how many electrons does that species have? Well, oxygen by itself has 8 electrons, and then the 2 minus means that it has a charge of 2 minus. That means it's gained 2 more. So O2 minus has 10 electrons. F minus, how many electrons does that have? Well, fluorine has 9, and then if we add another electron, the minus, that's 10 also. So neon also has 10. And sodium, how many electrons does sodium, not just sodium, but sodium plus have, a positively charged sodium, all right? Sodium itself has 11 electrons, but if it has a positive charge, that means it's lost an electron, so it has 10. So that means that the first one there, oxygen, fluorine, neon, oxygen, O2 minus, the F minus, neon, and then the sodium plus, that one should be isoelectronic. Let's take a look at the other one. B5 minus, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It has the same number of electrons as neon, B5 minus. Silicon plus 4, or minus 4, silicon minus 4, that has the same number of electrons as argon, but those are not the same number of electrons as each other, so they're not isoelectronic. The next option, F minus, we said that that had 10 electrons. Chlorine minus, that has 18 electrons, so those aren't isoelectronic either. Sulfur, chlorine, argon, and potassium, they're all different atoms. They all have different electrons. They're not going to be isoelectronic. Iso meaning the same in terms of the number of electrons they have. All right, so that's how you answer that sort of question.